Hello, today I will start recording videos about the algebra part in the Olympiad mathematics, and the first one will be Cauchy Schwarz inequality. This is one of the most well-known inequality in the Olympiads. And this tells us that if we are given n real numbers a1 all the way up to an and n real numbers b1 up all the way up to bn, then a1 square a plus a2 square plus up to an square times b1 square plus b2 square, then up to bn square. This is greater or equal a1 times b1 plus a2 times b2 plus a1 times bn square. Today we will discuss three different proofs of this one. At first, notice that if we discuss this function aix minus bi square, clearly this number is greater than 0, because for every real number x, because this is some number square, and clearly this is itself each number is greater than 0, so their sum will be also greater than 0. Now look at what will we get. Clearly this sum equals I equals from 1 to n ai square times x square plus, not plus, minus 2 times ai times bi, I equals from 1 to n times x, then plus bi squares, I equals from 1 to n bi square. And we know that this number is always greater than 0. So this means that if we look at this equation in terms of x, this is quadratic equation, so its discriminant must be less or equal to 0. And what can we say about this discriminant? So b square must be less or equal 4 times ac. b is, in our case, 2 times ai times bi. c is sum of the bi squares, and a is sum of the ai squares. So now let's write what will we get. So 4 times this product into square, this sum into square, ai times bi, I equals from 1 to n. This number is less than 4 times sum of the ai square times sum of the bi square. I equals from 1 to n, equals from 1 to n bi square. And now look at, if we cancel out 4s, then we will get the inequality what we wanted to prove. So we have proved Cauchy Schwarz inequality. So this was all we want to prove. Now let's move to the second case. The second one is about the arithmetic mean and geometric mean. If you don't know this inequality, we will consider this one for the next video. So if we are given two numbers a plus b, this is always greater or equal 2 times square root ab, if a and b are positive numbers, positive reals. And in this case we will discuss a1 square over product of ai squares, I equals from 1 to n, plus b1 square product from I equals from 1 to n bi square. By using this inequality, we know that each term will be positive, so there we can write this AMGM. So this must be greater than 2 times square root a1 b1, a1 square b1 square, so this will be a1 times b1 over square root from the product of ai square times bi square. I is from 1 to n also. And look at, if we write this for every I, ai square over sum of the squares, ai squared plus bi square over n equals from 1 to n bi square. This must be more than, greater or equal 2 times ai times bi over square root from the sum of the squares of ai times sum of the squares of bi. So we can write this inequality for as many numbers as we want. And if we take all ai's and bi's, then sum of these numbers will be clearly 1, and some of these numbers will be clearly 1 also. So if we sum all this left hand side, we get that 2 is more than equal sum of the j equals from 1 to n, 2 times aj times bj over numbers squared from the numbers I equals from 1 to n, ai squared times bi squared, sum of the squares of bi. So now we get what we'll get. Look at carefully. 2's will be cancelled out, and if we take both sides, we know that they have all these fractions common denominator. We can multiply both sides by this one, and we will get that sum of the square root from a1 square, I equals from 1 to n, ai square times bi square, sum of bi from I equals 1 to n, bi square. This number is clearly more than sum of the ai times bi, I equals from 1 to n. And now we need to take both sides into square to get the initial Cauchy equation. So we get that if we take this into square and this one also square, sum of the ai squares times sum of the bi squares, I equal from 1 to n bi square. This must be clearly more than sum of the ai times bi from 1 to n into square. And so we have proved by using the arithmetic mean and geometric mean. And last proof is by using vectors. If we are given any vector x in n dimension and its coordinates are like a1 x vector equals a1 times a1 a2 all the way up to an, and y vector its coordinates must be b1 b2 up to bn. And if we take their scalar product, then their scalar product would be like size of x times size of y times cosine of alpha, and this cosine of alpha is angle between them. How can we compute the size of any vector x? To compute the size of x, we need to take the square root from a1 square plus a2 square all the way up to an square. Similarly, size of y will be b1 square plus b2 square all the way up to bn square. And how can we compute this scalar product? X times y, scalar product. This equals a1 times b1 plus a2 times b2 all the way up to an times bn. So what will we get after taking both sides? So sum of the ai's, I equals from 1 to n, ai bi, this equals size of x, so square root from a1 times a1 square plus a2 square plus an square times b1 square plus b2 square all the way up to bn square times cosine of alpha. And what do we know about the absolute value of cosine of alpha? This number has absolute value of cosine of alpha less or equal 1. So we can assume that, or we can conclude that this left hand side, only this number, must be greater or equal to the left-hand side. And this is clearly Cauchy Schwarz inequality. And now look at when can be the equality occur. Then cosine of alpha equals 1. So alpha must be 0. So they must have the same, they must be on the same altitude, same direction. Like if the first one is like x, then y must be also on the same direction. So it must be minimized of x. We can see that this inequality must be from the first one also. When can we say about this function equals 0? This function will be equal to 0 if x equals a1 over b1. X must be also a2 over b2, all the way up to an over bn. So we will see that equality occurs then fraction of ai over bi is always some constant number. So what can we learn from this video is that this Cauchy Schwarz inequality is always correct, and equality occurs then fraction of ai and bi is always a constant number for every I from 1 to n. So this was all I want to discuss for today. If you want to discuss some theorems or inequalities, please write in the comments, and don't forget to like and subscribe my videos.